Inés, ¿me pasás los permisos?
Hola, Noel, lo está manejando ahora Nico.
Ah, listo.
Ya dejamos así no hacemos más lío. ¿Vale? Okay, Pablo, whenever you're ready.
Okay, so it is a great pleasure to introduce Eric Cator, that will talk about the contact process, that is a famous process in particle systems. I met Eric around 15 years ago. He came to Buenos Aires. He was interested in the same things that I was working for some time, and he had a very nice. Sorry?
I came to Sao Paulo to visit
Sao
you.
Paulo, yes. Yeah. He was working in this Hammersley process with Grönebom, had very nice results on that. But in fact, Eric, I guess, started as a statistician. And so, and then he entered in probability from this point of view of statistics, that was very, very nice. And then I met Eric several times in several places, and it is a great pleasure to have him here to talk about the contact process. So, yes.
Thank you very much, Pablo. And also thanks, Ines, for inviting me. In fact, I was hoping to visit Buenos Aires this year, but well, for obvious reasons, that didn't happen. So I'm very happy that I have a chance to talk about my work well, through Zoom. It's also nice. I also have met several of you, I think 2 years ago. So it's nice to see everyone again. And indeed, I will talk about the contact process on random graphs. And this is joint work with my colleague Henk Don, who's also in Nijmegen, the Radboud University. Okay, that doesn't work. Okay. I'm trying to skip to the next slide. It's somehow not working. Okay, so well, the contact process almost needs no motivation in this time, since it's actually a model for the spread of information or infection or gossips on large networks. So we try to have a mathematical way of formulating the spread of a virus on a network, and I will try to explain how this works and what kind of consequences this has. I don't want to make any claim that this work is of any relevance in fighting the corona crisis or something like that. That's, I think, most certainly not true. It is, the model itself is somehow relevant, I think. It has, you could use it to model the corona spread, for example. But what's much more important is how to get the network right and how to get the different rates correct, and how do you do time evolving in that. So there are lots of more relevant questions than the things that we can do mathematically at this time. So we will actually keep it relatively simple and still see that there are enough problems to deal with. Okay. I have some problem going to the next slide for some reason. My apologies. So what is the model definition for the contact process? We work on a graph, and we have a set of vertices and a set of edges, and the n denotes the number of nodes. And the nodes, they can be either infected or not infected. So you could think of them as people, these nodes. So on this graph, there's an adjacency matrix, Aij, which is 1 if I and j are connected through an edge and otherwise not. So we only look at undirected graphs. And so as I said, the nodes are either infected, and when they're not infected, they will be susceptible. So in this model, which is not that common, but in this model, when you heal from your infection, you again become susceptible. and then you can become infected at a later time. And it's this kind of feedback loop that makes it quite hard to analyze mathematically, this whole model. So there's several decades of work making very little steps all the time in analyzing this model. And the states of every node changes over time. Now, the local rule for the time evolution of the model is relatively simple. So this means that if we have an infected node I and a susceptible node J, and they are linked, then there will be an infection from I to J at rate tau. So this means that tau times per second, I tries to infect node J. And so when tau is small, it happens rarely, and when tau is very high, it tries to infect quite a lot. And also, as soon as J is susceptible and it gets this infection signal from I, it will get infected. So that's one step that could happen. You could have an infection. The other step that could happen is a healing. So people heal from the infection. And in our model, everyone will heal at the same rate, and we will call this rate just 1. So on average, once per second, nodes will become healthy again. Okay. Now these are the local rules, and we can then write this down more formally into an actual Markov process. So on a Markov process, you have a state space. These are the possible states of the process. And we will look at a discrete state space, but we will have continuous time for this process. So what does this mean? Well, the possible states of the process are simply the set I of infected nodes. So if I tell you which of the nodes are infected, then I've told you the entire state of the process. And that means that the state space are just all the possible subsets of the nodes. So the Markov process works on this state space. And then there are transition rates. So what is special about a Markov process? If you know the current state, then the entire distribution of the future is fixed. So it doesn't matter how you got to a certain state. It only matters that you are in a certain state. That's the only relevant thing. So all I need to do is tell you, if you are in a certain state, what are the possible changes that can happen? And that's written down in the transition rates. So this is just actually a translation of the local rules I already told you. So what does it mean? So if I'm at state I can move to state I joined union with the set J. That is for J, which is not in I. So that means that J is susceptible because it's not infected. So this means that J gets infected. That's what this transition means. We used to have the set I, and now J joins the set of infected nodes. And the rate with which this happens is the following. You sum over all infected nodes. You check whether that specific node is linked to the node J, and then you add them all up and you multiply by tau. So that's the total rate with which J can get infected. And then the second thing that could happen is a healing. So for every J in the infected nodes, what could happen is that the state changes from I to I minus J. And this happens with rate 1 because every node heals with rate 1. And so this Markov process moves through this state space of all possible subsets, and it goes back and forth, basically. If something is not clear, please feel free to unmute yourself and ask a question. That would also help me. I know this is a general audience, so I can imagine that not everything I say rings a bell with everyone. So please ask questions if you feel like it. Yeah, now the state space of this Markov process is very complicated. The set of all subsets has very little usable structure. It's difficult to dominate things. It's not so easy to work with. And that's one of the reasons why this particular Markov process is still being studied after several decades. And you might even say that relatively little has been proved about this, about these Markov processes. And I will talk about that on the next slide. Now let's think what we do know about this Markov process. So first of all, there is one, and actually there's exactly one equilibrium state, which is actually the state, the empty set. And this is like a final state, in fact. As soon as I is empty, it means that nobody is infected, and then the whole infection has died out and nothing happens anymore. So once you once you reach the empty state, that's it. That's the end of the process. So in that sense, it's not very interesting. It doesn't have like an equilibrium or like an interesting equilibrium, because you always end up in the empty state. And so there's almost surely there's a finite extinction time for a finite graph, and we call it T of n. And to be definite, we will just start from a full infection and then wait until the whole infection has died out. Now, so this is not so interesting. It will always die out. However, there is an interesting phenomenon, and it's more clear with infinite graphs, but it's also present in finite graphs. And the phenomenon is that if the infection rate tau is too large, then the extinction time is enormous. It's in fact, it grows exponentially in n. So if you have 100 nodes or 1,000 nodes, all of a sudden you have to wait an astronomical time before something happens, before you die out. This is called metastability. So it's not a true stable distribution that you're in, but it's almost that, because you have to wait such a very, very long time before you're out of it. And we will also try to make this more explicit, what this means is metastability. But for now, and the intuition you should have is that if tau is large enough, we talk about metastability if the extinction time, the expected extinction time, grows exponentially in n. So then there can be several questions. So does this metastable state exist? Or will, for some values of tau, the thing will die out very quickly, and for others it will stay for a long time? And when is this kind of phase transition, this crossover between these two things? In case of the existence of a metastable state, what does it look like? What happens during this enormous amount of time? What does the process do? Does it have some kind of stable behavior? And can we describe this? So those are interesting questions. And what I would like to do now is just illustrate a little bit how this works. And let's see if it works out. So I hope that you now all see my R window. Is that correct? I guess so. Okay, so what I want to do is I want to show you a small...
We see your window, Eric.
Say again?
We see your window.
Excellent. That's nice. So what I've done here is write a little program, and I will start with an Erdős-Rényi random graph. An Erdős-Rényi random graph means that I have 100 nodes, and every edge, every possible edge, so those are quite a lot, I don't know, almost 5,000, I guess. Every possible edge has a probability of 5% to be present and 95% to not be present. So I just, for every edge, I randomly flip a coin and I see if it's present in the graph. And then I make this graph, this random graph. I've done that already. So that's my A is the adjacency matrix of the graph. Then I choose an infection rate. In this case, I choose 0.2. And I look for 100 seconds and see what happens to my number of infected individuals. So now you see a picture here on the right bottom part. It started off at 100 infected because I did a full infection. And then you see that after 15 seconds or so, the whole thing has died out. So let's do it again. Now it's almost the same time. Now it's sooner, a little bit later, but in a relatively short time, the whole infection will die out with this low tau. So now I increase tau and see what happens. So I go to 0.3. And I run the program, and you see that it still dies out. It takes longer. And this was relatively quick. A little bit longer again. And this one didn't die out within 100 seconds, but most likely it will die out within the next 100. So these are different realizations of this infection. And then I can increase a little bit more. So let's go to 0.4. This. And what you see now is that it didn't die out. And also, on average, it's about 40 infected people of the 100. And this we fluctuate around this average. So let's do it again. And you basically see the same picture. There's some fluctuation around, let's say, about 40. And it doesn't seem to die out. So I can illustrate this. I will do one more thing. I will go for 500 seconds. Then we have to wait a little bit. So what you see here is some evidence of metastability, because there seems to be a stable behavior. Here there's 500 seconds and still it didn't die out. You see some stable behavior around 50. And in some places, you go down a bit more or you go up a bit more. So you could view this as fluctuations from this stable distribution. And the idea is that these fluctuations will get bigger if you wait for a longer time. If you wait for an exponentially long time, it will get so big that you actually reach zero, and then you can never get back. So it's like you reach the top of the mountain and then you stay there. But if you don't reach the top, then you drop down again. That's the way you should see it. And so in this way, there is some metastability, and it's interesting to know, what does this metastability look like? So for example, I can try and make a histogram of these numbers. And if you have a little bit of imagination, you could kind of see around 35 maybe, there's some kind of normal distribution appearing. So it seems that the number of infected individuals at a large time will have some kind of normal distribution, except when you have by accident reached zero, and then the whole thing has died out. So this could be some type of description of the metastable state. Are there any questions about this simulation? Because otherwise I will go back to the slides. No? It's clear?
I have a question.
Okay.
So you started with how many people infected at the beginning?
I started up with 100 people infected.
Everybody?
Yeah, everybody.
Okay. Thank you.
And you can see it here in the picture.
Okay, yes.
It just drops down very quickly.
Yeah.
So the idea is that if you have a lot of infected people, then infecting a new person is actually quite slow, because there are only very few susceptible persons.
Yes.
But the healing rate is quite high because there's so many infected people. So there's like a drift going down. And in this case, when you're the other way around, so when you have very few infected people, the drift is back up, because few people infected, they have neighbors and they can infect all their neighbors, but the healing rate is very low because there's so very few people infected. So then there's a drift up again. And that kind of causes this stability that you see here.
Would you like to comment about the cluster, the big cluster of the graph or something?
I'm not sure what you mean.
Because this graph is, there is a big cluster, right? They are connected, or this infection is going.
Yeah, so it's true that in these finite graphs, there usually is like a connected cluster, and the disconnected parts, they will die out very quickly, usually. And only the connected cluster will have some infection. However, that's not relevant for our method, and we will not use it.
Ah, okay. Okay, thanks.
Okay. So I will try and go back to my talk. Now, did it work out? Everybody can see my talk again now?
We see the talk now.
Excellent, thank you. Okay, so let's see, let's review a few things that are actually known about this contact process. So the probabilists, they started working on this model in the end of the 70s, beginning of the 80s. And they started actually on infinite graphs. So let's say ZD or infinite trees. And then the question was, if you have a certain infection rate, does the model have a positive probability of surviving, or will it always die out? And you can imagine that on an infinite graph, the infection can just grow and grow and never die out. That's possible. So then it survives. Now, Holly and Liggett, they actually prove the existence of some critical Tor, and they have also some bounds on this Tor. So that means that, for example, on the lattice Z, there exists a critical Tor below which it will die out almost surely, and above which there's a positive probability of survival of the infection. There's a unique number. And then much later, Bezuidenhout and Grimmett, they prove that at criticality, so if you're exactly at the critical Tor, which in fact is unknown, the critical Tor for these ZD ones are unknown. And in fact, almost for any graph, they are still unknown, these critical Tors. But Bezuidenhout and Grimmett, they prove that if you're at this critical Tor, then the process still dies out. It does not survive. Pimentel had a very nice contribution about trees. So if you have regular trees, for example, binary trees, he gives quite precise bounds for the critical Tor. And in fact, he shows that there are two critical Tors for these trees. For one Tor, so if Tor is very small, everything will die out. And then if Tor is very big, it will survive in such a way that the root, where for example, the infection starts, the root will remain being infected for all times. So it will get infected an infinite amount of time. And then there's some in-between value where actually the root will heal and stay healthy after finite time, but the infection still goes on further up in the tree. So the infection survives an infinite amount of time, but it's further and further up in the tree where, of course, there are more and more leaves and branches, and it has more space to survive, but it will not be able to get back to the root. So that's like weak surviving and strong surviving. So that's that's interesting behavior on these trees. Then later on, people also started to look at finite graphs, especially in the more applied literature, and people were interested in, when will this metastability phenomenon, when will this occur? Can we say something about the limits on Tor for when do we have metastability and when will it die out? And can we get bounds on that? And then mean fields methods were introduced, and there were several conjectures for the critical Tor. And also, if you're above this critical Tor, so there will be infection, there will be a metastability, what is the expected number of nodes? Now you should think of my simulation. In the last simulation, the expected number of nodes was something like 35. So can we calculate this 35? Is there a way to do that? That's what's been done in the applied literature. And then a surprising result came by Chatterjee and Durrett. And it said that if you have a graph and the degree distribution of the graph has a power law, which means that the probability that the degrees are bigger than x is like x to the minus alpha. So it doesn't go down very quickly, only polynomially. And that means that in such graphs, you will have nodes with a lot of degrees. And Chatterjee and Durant, they proved that the critical value for these graphs is actually 0, which means that for any positive infection rate, you will have metastability. And the expected survival time will be exponential in those cases. And then Mountford and Valesine and Murat and Shapira and others, they improved these results. They considered bounded degree graphs and regular graphs. And the main contribution was to show that in these kind of heavy-tailed degree distributions, you always get survival of the contact process. Okay, and then more recently, there were very interesting results also by Durant, but also by Sly and his, Alan Sly and his collaborators. So Durant and Wang, they proved that if you have a Galton-Watson tree, so what is a Galton-Watson tree? For those of you that do not know, you start at the root, and then you have a number of children which is distributed according to some distribution, and all these children, they also get children according to the same distribution. So a Galton-Watson tree is kind of defined by the offspring distribution, as they call it. And then you make a tree with it, and then you look at the contact process on that tree. And Durant proves with Wang that if the degree distribution is somehow heavy-tailed, and that means that any exponential moment is plus infinity for every c bigger than 0. So you always have infinite exponential moments, and this kind of suggests that you have heavy tails. Then the critical tau is 0. So for any positive tau on this Galton-Watson tree, the infection will survive. And then Sly and his collaborators, they proved that this is actually if and only if. So that means that if there exists an exponential bound, so then the tail is not so heavy of this degree distribution. If there exists an exponential bound, then the critical tau is strictly positive. So there is some tau for which you get, above which you get survival, and below which the thing dies out, in fact, in linear time. They also prove this. So this is a very strong, strong result. And if you can do this for the Galton-Watson tree, in fact, you can also do this for the Erich-Renyi graph, for which I already talked about, but also for what they call the configuration graph. And I will come back to that later. So these results on trees are relevant for general graph models. And the reason is that if you look at a graph locally, so you start at a point, then you look what are the neighbors and what are those neighbors, and then you kind of build up a network like that by looking at the local neighborhood of one node, then you can imagine that this thing looks like a tree, especially if you don't have too many degrees. Yeah, because there are lots of nodes and only a few outgoing edges. So the chance that you see the same node is very small in these random graphs. And that's why these local neighborhoods, they look like trees. And Sly and his collaborators were able to use this fact to show that their result on trees actually implies something for Erich-Renyi graph and configuration graphs. So I call this a local analysis of the contact process. They could control things locally, and then they can get results. Now, the result that I will talk about today by Henk Don and myself, we actually look at more global phenomenon. So we give a global analysis. We don't look locally. And the advantage we have is that we get explicit bounds on, for example, for which tau does there exist survival. So explicit bounds on the critical tau. Also, the methods are applicable to more general graph models. However, there's also a drawback. We cannot cover the full range of the local results. So Sly and his collaborators, they prove things for graphs that we cannot handle. These graphs are kind of beyond our method. And I will get back to that later. Okay. So now to start the kind of more technical side of this talk, I will first look at the complete graph, which is somehow it's in fact much easier than a general graph. So what is the complete graph? You have n nodes, and all the possible edges are actually present in this graph. And then you can imagine that the state space of the contact process is which set of nodes is infected. But in the complete graph, every node is interchangeable with every other node. So all of a sudden, it's not relevant anymore which nodes are infected. The only thing that's relevant is how many nodes are infected. And it doesn't matter where they are. So that means that if you define X as the number of infected nodes, then X itself is a Markov chain. And that makes the whole analysis, well, kind of trivial compared to the full contact process. However, the phenomenon of metastability is still present here and can be analyzed quite precisely. And also, I will show this analysis for the complete graph because it's relevant for our approach of the problem. So what can we say? The number of infected nodes, X, has a very simple state space. It can vary between 0 all the way up to n. And if I want to study metastability, what I will do is I will forbid the transition from 1 to 0. So if there's only one node infected, I will not allow it to heal. And this means that there's no absorbing state anymore for this Markov chain. And then there's actual stability. You actually can say that there's a stationary measure for this Markov chain. And you can somehow calculate it. And what you see here are the so-called detailed balance equations. So you look at what is the rate with which you go from state k to k plus 1. So let's think about that. K means you have k infected people. That also means that there are n minus k susceptible people. That means that the total number of edges between the group of infected and the group of susceptible people is equal to k times n minus k. So multiply this by tau, and you have the rate with which you will go up by 1. So this is the total infection rate, tau times k times n minus k. And if you're at k plus 1 and you want to go back, well, what has to happen is that someone has to heal. There are k plus 1 nodes infected, so the total healing rate is k plus 1, which it says at the bottom. And detailed balance is just this equation that I have, well, I'm not sure if you can see my mouse, but anyway, here at the third point. So pk, the probability of being in k, times the rate of going to the right has to be equal to pk plus 1 times the rate of going to the left. And you can actually solve this. And it turns out that you get interesting results if your infection rate tau is of the order lambda over n. Then something interesting happens in this case. So let's see what that is. It turns out that if lambda is bigger than 1, so that means that the infection rate is big, then you can bound the P1 that I've just defined. So that's the stationary probability of being in 1. And it's very, very small. It's exponentially small, in fact. And that means that the time you take to get there, so suppose you start with n infected nodes, the time you take to get to 1 infected nodes is bigger than e to the constant times n. So already you see that you get exponentially growing extinction time. And you might say, well, this is for this kind of, this is not the real contact process because I forbade the transition between 1 and 0. However, it's not hard to realize that as long as you don't reach 1, the two models are in fact the same. Because you never had the possibility of going from 1 to 0. So these models are exactly the same until the moment that you reach 1. And this moment already takes an exponential amount of time. And so this, in fact, does prove that the actual contact process has an extinction time that grows exponentially. Now, we can say a little bit more in this case. We can also say that if you look at the stationary distribution before an exponential time, let's say after a linear time, then the number of infected nodes is in fact approximately normal. And we can even write down what is the expectation and what is the standard deviation. So the expectation is linear in n, and the standard deviation is of the size square root of n. So the fluctuations are in fact quite small, or the square root of n compared to n. And you can actually prove this on the complete graph for the contact process. So we have a description of the metastable state in that case. Now, on the other hand, suppose lambda is smaller than 1. So the infection rate is lambda over n. We looked at lambda bigger than 1. Now lambda smaller than 1. Then there's a nice trick that you can do. You can look at the expected number of infected nodes at time t. And then if you take the derivative of that, you just get, in fact, this is a little bit technical, but for the probabilist, it will be somehow clear that you can look at the rates with which you can go from x to x minus 1 and from x to x plus 1. And these rates, they tell you something about the derivative of the expectation. And it turns out that it's exactly this formula that it says on the first line here. And then you work it out, and then there's a problem because you get the expectation of x, but you also get the expectation of x squared. And we don't know that yet. However, we can just forget about the expectation of x squared because it's positive. And then you see that the derivative is smaller than a constant times the expectation of x. And this immediately gives you an exponential bound on the expectation. So we know that the expectation of the number of infected people goes down exponentially fast in this way, n times e to the minus 1 minus lambda times t. So that's very quickly, and you can use this, it's not so hard, to show that the extinction time, the probability that the extinction time is bigger than t is in fact smaller than n times e to the minus 1 minus lambda times t. And that means that the extinction time is of the order of log n. So there's a very, very clear phase transition. Lambda smaller than n, you get something like log n and you will die out. Lambda bigger than 1, and you get exponentially growing extinction time. So it's quite remarkable. In fact, the interval, the change interval, let's say, from smaller than 1 to bigger than 1 is, I think, of the order 1 over n in this case, or 1 over square root n. And that's like the tightest interval that you can get. So this complete graph has somehow an extremely small phase transition. But that's not so relevant for now. Okay. And what we want to do is we want to show similar results, at least for the exponential survival, similar results for general random graphs, and in fact also using similar ideas. So that's what that's what this slide is about. So we now look at the contact process on the Erdős-Rényi graph. And I already explained what the Erdős-Rényi graph is. You get n nodes, and each pair ij is connected with an edge with probability p, and in this case, p can depend on n, so pn. And then the contact process has state space I, where I is a set of infected nodes, but I'm interested in a function of I, namely the number of infected people. So I call that x, the same way I did for the full graph. So x is the number of infected people. And remember, in this case, x is not a Markov process, because it's not enough to know how many people are infected. You need to know which ones, because the graph is not homogeneous. So you need to know which ones are infected to know how many will be infected in 1 second later, let's say. Okay. Now, I can write something down for this x. I can write down the rate of change for this thing. So let's say the adjacency matrix for the Erdős-Rényi graph is A. And let's say I'm in state I, so I know what the infected set is. And then I'm wondering, at which rate will I change from x to x plus 1? So what does this mean? This means that there will be an infection instead of a healing. If there's an infection, the number of infected will go up by 1. And what is the rate with which this happens? Well, I look at the number of infected nodes. So I sum over all the infected nodes. Then I sum over all the susceptible nodes. And I see which of these pairs I and J are connected. So I have this double sum here of the Aij, and that's just the total number of links between the set of infected nodes and the set of susceptible nodes. The total number of links, if I multiply that by tau, that's the rate with which I will go up, with which I will get an infection. And going down is much easier because there's X people infected. They all have healing rate 1, so the total rate of healing is X. Now here comes the idea that we have exploited, let's say. The idea is that this number, this Li, so remember, Li is the number of links from the infected set to the complement, which is the susceptible set. So the total number of links in the graph. And what I want to do is I want to bound this number of links uniformly over all possible i's with the same number of nodes, namely X. If I can do this, if I can bound this uniformly over all I, then I have a bound of the rate with which X goes up by 1, and I have an exact formula for the rate with which it goes down. So what I can do then is I can compare the process X, which is not a Markov process by itself, but I can compare it to a birth and death process through these bounds, and then I can couple these two things, and I will know that X is always smaller than this birth and death process, or always bigger, one of the two, depending on the bounds. And this might be enough to prove exponential existence of the contact process. So let's see how this works. I start with the easiest case. This is the supercritical case. Supercritical Erdős-Rényi, it means that n times Pn goes to infinity. You should think of n times Pn as the expected degree of one node. Yeah, because if you have one node has, there are n-1 other nodes. And how many edges does this one node have to these n-1 other nodes? Well, in expectation, that's exactly n-1 times Pn. So n times Pn is something like the expected degree of each node. And supercritical case means that this expected degree grows, it goes to infinity. That's the case we are looking at now. So you have a growing number of neighbors. And the approach is the following. I look at a fixed I, a fixed set of infected people, and I assume that they have k nodes. So a fixed I with k nodes. And what I was, and now suppose that this set is infected, this I, how many links do there exist between I and the complement of I? That's what I'm interested in. And you can imagine that this number, this L of I, has simply a binomial distribution, because there are k nodes in I, and therefore there are n minus k nodes in the complement, and therefore the total number of edges, possible edges, is k times n minus k, and each of these edges is on with probability p. So you get a binomial distribution. So what I'm going to do is I'm going to bound the probability that this L of I is very small or very big, and I'm going to bound it so much, so I'm going to make the probability so small that even if I multiply this with the total number of i's, so the total number of i's with size k, even then the probability is small. That's the trick. So this is, in that way, I will get a union bound. Yeah? And that's the result that's set that you can see here at the second point. If you fix rho smaller than 1 and fix a gamma bigger than 0, then with very high probability, it will be true that for every k in this interval, but also for every set I with k nodes, L of I will be in between these two numbers. And these two numbers, you should think that P times K times N minus K is the expectation for L of I. So if I multiply it by rho, it will be smaller than the expectation. And if I multiply it by rho minus 1 to the minus 1, it will be bigger than the expectation. And my L of I will be within these two bounds with very high probability for every possible set I. And that will help us because no matter what the infected set is, the rate with which it goes up is always bounded by these bounds that I have found here. And therefore, I can now define birth and death processes x tilde that have the corresponding rate to go up and to go down. And then I can couple these such that either x tilde is always smaller than x, and then I have to use the lower bound on Li, or x is always smaller than x tilde, and then I have to use the upper bound on Li. One of the two. And then now I only need to analyze these birth and death processes, and then I can say whether there's exponential survival time or not. So here's the theorem for a supercritical Erasgeni graph. It says that if tau is lambda over n times p, for any lambda bigger than 1, then Tn will grow exponentially in n. So this is the critical value of tau for these supercritical Erasgeni graphs. And we can say even more. This has not been proved yet, but this is like a conjecture that we have. And I think, well, we already know that if n times Pn is controlled enough, so it has to go to infinity at a certain speed, then for sure we can prove this. So we even know that our x has before this exponential time, it will have a normal distribution. Now this is an optimal result in the following sense, that if lambda is smaller than 1, then in fact no exponential growth is expected. And we can say even more, we can use the same approach we did for the full graph. Remember that we had this expectation of x, we took the derivative, and then we had some bound. Now in this case we can do it as well, but we have to do it for the vector of x's. So it's slightly more complicated, but it's the same idea. And it turns out that if you look at the adjacency matrix in these supercritical Erasgeni graphs, they have a largest eigenvalue, which is very close to n times p. And that means that tau times the largest eigenvalue is smaller than 1 in this case, because it's close to lambda. And that means it will die out exponentially fast, just like before. And you in fact get a logarithmic extinction time. So for lambda bigger than 1, we get exponential growth. For lambda smaller than 1, we get logarithmic growth. So it's very much like a complete graph, in fact, except that the effective infection is p times tau instead of tau itself. And that's because some of the edges are lost. So it's not the complete graph, it's the complete graph with edges lost. And that means that the infection effectively is lower than tau. But in another sense, it's basically the same. So you don't see the local structure of these supercritical Erasgeni graphs. The contact process just behaves like it's on a complete graph. Okay, so that's nice. These are nice results, and they're also kind of unique for our method. So these are the first results for supercritical Erasgeni graphs. Now we go to critical Erasgeni. We don't have to go to subcritical, because then there are no large clusters. We only have some kind of scattered little clusters of nodes, and they will die out very quickly. But critical Erasgeni graph is still interesting. So what does this mean? It means that the expected degree for each node is constant. So I take my p to be equal to sigma over n. That's what I will do. Okay. And then I need to have a similar approach. So I take my I, and I say, okay, suppose my set of infected node has size k. What can I say about the links between I and I complement? How many links do I have? And in this case, I only want to have an upper bound on the number of links, because then I have a lower bound. I'm sorry, I want to have a lower bound on the number of links, because then I also have a lower bound on the drift going up, so that I get more and more infections, which is good because I want to show that the extinction rate is exponentially growing. So I want to have more infections, or lower bound on the number of links. And the way I do this is, well, also for this critical heterogeneity graph, I still know that this L of I has a binomial distribution. So it's not so hard to write down an explicit formula for the probability that L of I is smaller than rho times the expected value for L of I. And it's given by this formula. And then there's a G of rho, and G of rho is explicit. Rho log rho plus 1 minus rho. So I have an explicit formula for this probability. Now this is for a fixed I, but I want uniform control. So I want to be able to control this for all I of size k. And how many are there? Well, there's the binomial coefficient. It's n over k, n over gamma n. And this number is upper bounded by e to the n h of gamma, where h of gamma is the entropy for the number gamma. So the formula is here. So what I can say is the following. The probability that there exists some set I of size k, which has fewer links to the complement than rho times this expected number, the probability that there exists such an I is smaller than e to the n, and then there's this red formula, h of gamma minus sigma gamma rho gamma 1 minus gamma. And of course, I want this exponent to be negative. I want to have a small probability for some gamma and for some rho. And if I can do that, well, then I just want to make sure that the infection rate, so the rate with which the number goes up, is a factor larger than the healing rate. And that's what it says at the bottom here. The infection rate will be rho times p times k times n minus k times tau. Because that's exactly this bound here that we have in the probability. And that has to be bigger than the healing rate k. So then I get this kind of formula for tau. If tau satisfies this, then I expect an exponential growing rate. As long as this red formula, h gamma minus, well, all that stuff, is negative. That's what I need. Now here comes a drawback of our method, because it turns out that this thing is not always negative. I can only get it to be negative if the sigma, which is the expected degree, is bigger than 4 times log 2. And it's not so hard to check that this is that we need this. So we can only look at critical heterogeneity graphs which have an expected number of nodes bigger than 4 times log 2. And if we do that, then we can prove that there exists a tau such that t is exponential in n, and we even have explicit bounds on this tau. And we can do a little bit more. We can also show that this critical tau for large sigma looks like 1 over n times p. And that somehow corresponds to the critical tau in the supercritical heterogeneity graph. So if sigma is very big, if the expected degree is very big, then things start to look like supercritical. So that's also an interesting result. But the drawback is that we need sigma to be bigger than 4 log 2. And in fact, Sly and his collaborators, they could show that if sigma is bigger than 1, then a critical tau exists. But they don't have any bounds on tau. And that's what you want. That's what you would expect, that sigma needs to be bigger than 1. Okay. I see I only have 3 minutes left. So somehow I took too long, I'm afraid. Let me see how I can do this. Yeah, so it turns out that our approach is also possible for what they call the configuration model, or the configuration graph. And I will explain to you how the configuration model works, and then I will show you some results that we can get. So the configuration model, it has a degree sequence. So for every node, I sample a degree from some fixed distribution. And these half edges or stubs are kind of linked to this particular node. So every node gets their own number of half stubs. And once I've done this for every node, I randomly connect all these half stubs to form actual edges. So I just pick two at random, connect them, and then I pick two new ones and connect them again, and then I get a connected graph. And there's a slight problem if you have an uneven number of nodes, but then that one just doesn't get connected. That's fine for us. It doesn't really matter. Yeah, so this is the model. We have a degree sequence, an IID degree sequence, and then you get half edges from every node, and then you just link them up randomly. And the approach that we will take is the same. We will fix a set I, and we will look at the number of links between I and the complement of I. And we expect a linear number of links. So I want to bound the probability that the number of links is smaller than some rho times n, rho being smaller than the expected fraction. And this needs two steps. You need to lower bound the total number of stubs. By accident, you could have very few half edges. And then, of course, you also have very few links. So that's step one. You need to make sure that doesn't happen. And the second thing that you don't want to happen is that if you have a given number of half edges, then maybe by accident, all the links within I are, all the half edges within I are linked, and all the half edges with I complement are linked, and there are no cross links. So you have very few cross links. That's in principle possible, but of course has low probability. And somehow you need to combine these two things. And the way to do this is using large deviation theory, for those of you who have seen this. So I will not go into the details of this because I don't have any time anymore. It's interesting, but not very deep. All I want to say is this result that we have. So what does it say here? It says if you look at the probability that the links between I and I complement is smaller than rho times n, and then you take the log of the probability and you divide by n and you take the lim sub. So this is typical large deviation stuff. For people who know this, this is how you kind of approach the large deviation probabilities. And we can bound this lim sub by a function psi of gamma rho. And psi of gamma rho is made explicit in this formula below here with some explicit phi, and this capital R, that's the rate function corresponding to the distribution of the degrees. So it's also explicit. Okay. So this takes some work, and you need to adapt Varadant's lemma and some of these large deviation things, but it's not that hard. And then what do we want? Well, first of all, since you could rewrite this formula as the probability is smaller than e to the minus n times psi. And then you have to multiply this by the total number of sets. So what we need is that psi is bigger than the entropy h of gamma. Otherwise, it's a useless bound. So that's the first thing we need. And then once you are able to do this, you want to choose rho over gamma as large as possible, because that gives you the best bound on the critical tau. So tau is like gamma over rho, and you want that to be as small as possible. Okay, and it turns out that we can do this. You can find rho and gamma such that this is true. And then once you have done that, you can prove that for certain sizes of sets, the links will always be big. The links between I and I complement will always be bigger than rho times n. And therefore, there will be an infection rate going up, which is bigger than the healing rate. And then you can guarantee exponentially growing extinction time. Now, there's some nice things going on here, but I will not tell you. It turns out that the same as with the Erasmus graph, we cannot handle every degree distribution. We need a condition on the degree distribution. And this condition is given here. It says that if the expectation of 2 to the minus 1/2 d, if that's smaller than 1/2, so here d is the distribution of the degree of every node. Yeah, because it was a fixed distribution. If this is smaller than 1/2, then we can find the tau, and we have explicit bounds for tau such that the extinction time grows exponentially, such that we have this metastability. And so this is kind of nice that we were able to, we had this complicated psi, but we were able to make an explicit formula for our d, explicit condition. And the condition, in fact, you can easily check that this implies that the expected value of d has to be bigger than 2. And this is enough to show that there is indeed a giant component in this configuration model. Now, again, here we see the disadvantage of our approach. We need this kind of stronger condition on d, whereas Sly and his collaborators, they only need the weakest condition on d, which is the fact that there exists this giant component. As soon as the giant component exists, they have that there exists a tau such that you have exponential extinction time. But they have no bounds on this tau, and we do have the bounds. So we cannot go all the way, but we do have explicit bounds with our relatively simple method. Okay, I will not do this. Yeah, so there are some conclusions and also some leftover research. And so for both models, we have sufficient conditions for exponential extinction. And also we have this Erasmus model and the configuration model, but we can go on. We have more models that we can handle with this method. So that's also interesting. It's kind of robust method in order to analyze random graphs. Now we know that the conditions are not optimal in the sense that they're not really necessary, but we do have explicit bounds. So that's also strong. We would also like to see when there is no metastability. So when will things die out very quickly? And Sly and his collaborators, they have results on this. And it turns out that it's much more relevant to look at the local behavior. If you want things to die out, you want to look at an infection at one node and see what happens. So that's kind of different from our methods. So I think we need a new approach there, or we'd have to follow Sly's approach. And also we want to determine the metastable distribution. So that's a question that hasn't been answered at all, except for the supercritical Erasmus. What does this metastable distribution look like? Does it look like a normal distribution? Can we say something about the mean and the covariance? And we were not there yet. Okay. So thank you very much. And the paper on this stuff can be found on arXiv, and we hope it will be published very soon. Thank you.
Thank you. Thank you very much, Eric. Very nice, very courageous to work with, to couple the contact process with the birth and death process.
Yeah. So nice it worked out. We were not so sure it would, but well, we got interesting results, so it's nice.
Okay, so is there? So maybe we have to clap then if you want to. Is there any question?
I have a question.
Okay. Pablo Grossman.
So, hi, Eric. How are you?
Hi. Good to see you again.
Yeah, good to see you. So, great talk. I enjoyed it a lot. Thanks.
Thanks.
I have a couple of questions. Maybe some of them are silly ones. So the first one is that all your statements are respect to the joint probability, respect to the randomness of the graph, and also the randomness on the process, right?
So the statement is that with high probability, the graph is such that the expected extinction time is bigger than some exponential. So we did split it up, in fact, the two probabilities. And the with high probability statement is about the random structure of the graph. And then the next statement is about, given the graph, what can we say about the extinction time?
I see. I see. And the other question, I guess now I understand your answer. Maybe this is a silly one. So are these methods useful maybe for a specific particular deterministic graphs, or it's just, I mean, all this?
In principle, they are. The problem is that, so what we did is we showed that if you take this random graph, then with high probability, the structure of the graph is such that for any large enough set, you will have enough links from the set to the complement. Now, if you have a way to check this for your deterministic graph, then that's fine. So if you have a way to check every set of a certain size K and see whether there are enough links to the complement, then the method will work. So I could imagine that if you have a deterministic graph with a very specific structure, for example, then you might be able to actually do this. Of course, you can imagine if you have a graph from real data, then it's very hard to check every subset of a certain size. You know, there are just too many, so you cannot do that. So you would have to think of some other way to do it.
Well, maybe you can have a condition that you can check on the graph to say that if you are going to have this behavior or that, right? So I give you the graph and you check.
Yeah,
No.
so I don't, well, you know, one way I see is just to look at all the subsets, but that's not feasible for a large graph. And other things, I'm not so sure if that's possible. Of course, if your specific graph has some structure that resembles random structure, then at least you might have a good idea that this should be true, at least for a range of sizes, because that's also how our method works. We can show this for a particular range of sizes of the infected set, but that's enough to get exponential time, because you know you cannot get out of this range already. And so and you can do this maybe also for a specific deterministic graph, that if you look at your sets and they're kind of big enough, maybe that will be true then.
Okay, thanks.
Sure.
Yeah. I have a couple of questions. One is about, you are working in supercritical graph, right? Because your page 15, you say critical in the title, but I think it's supercritical. The graph is supercritical, but it is critical is the contact process, right?
So maybe I don't know what you mean by a critical graph. And then,
well, the critical graph is when the expected number of things per node is 1.
Okay, so indeed, I use supercritical in the sense that the expected number goes to infinity, and I call it critical when it's finite.
Okay.
But
okay.
You're right that the critical tau only exists if the expected number is bigger than 1. The expected degree. If it's bigger than 1, then there exists this critical tau. If it's smaller than 1, then the whole thing breaks up and there's no critical tau. You cannot have exponential time.
Okay. So the other question, yes, it's clear. Your answer is clear to me. So about the invariant measure, in fact, you are talking about the quasi-invariant, right? The quasi-stationary.
Yes. So the type of statement that we want to make is that.
But it should coincide the two measures, right? They essentially, because you are supercritical, you are so far from the absorbing point that the invariant and the quasi-stationary should be essentially the same.
That's true. Yeah, they should be the same.
Now you are coupling this measure with the quasi-stationary or stationary measure for the birth and death process. And then you say, okay, for the birth and death process is normal distribution around the mean. And can you couple, in some sense, that the number of infected people will be normal also in the
we can do this. We can do this in what we call the supercritical Erasmus. And that's because our lower bound and our upper bound are so close together that it's enough to squeeze them and to have these two birth and death processes have the same limiting distribution. So that's why we're able to do that. But for example, in the case where, in the critical case, so the sigma over n probability, our lower bound and our upper bound are quite far apart. So we cannot squeeze it in, but we cannot say that it's normal and with a certain mean. We don't know how to do that. Our bounds are too coarse in order to get a result like that.
Yeah, really surprised. Yeah, surprising that you can do something, in fact.
Well, it was a little bit surprising. It's true. Yeah, I still remember very clearly. I was explaining someone, about this contact process, and when I was explaining it, all of a sudden I had this idea, and I was kind of flabbergasted. Thinking that this might be enough, and it worked out. But so it's not so strong that we can do everything, right? But we can do some things.
I guess, because how can you get to press them to get the normal also for the contact process? Well, I have to read the paper, I guess.
To get the normal, it's not in this paper. It will be a next coming up paper with a PhD student. But we can only, as I said, we can only do that for the supercritical heterogeneity.
Okay.
So you could imagine that somehow this is so close to the complete graph that there are just more options to
no, because the problem is that I think that you will get different parameters for the macroscopic normal that are dominating from above and below. How do you get the real normal that you have in the middle?
Because the bounds are so tight that they get closer together than the scale at which they can differ, let's say.
Okay.
And because the scale is like square root n, the fluctuations of the normal.
Yeah.
But their averages, they get much closer together. So that's good enough to get the right answer. I think that's why it works.
Sounds incredible. Yes. Very good.
You need p times n to go to infinity at a certain speed. So just go to infinity is not enough. Then there will be some space. But if they go fast enough, then the whole thing is so tight that you can actually do it.
Okay.
And that will be, I think, the first result on a description of the metastable state in the contact process.
Yes. No, it's very strong. Yes.
But we can only do it for these kind of very dense graphs.
Okay.
Because you have a lot of control in that for these things.
Right? So almost a complete graph, you mean?
That's right. Yeah, they're almost a complete graph. That's what I mean. Now, so for example, the physicists, they use these mean fields models, and they were wrong at some stages. It gave the wrong conclusion, these mean field things. But for these type of graphs, they're very, very good, these mean field approaches. And we can just kind of make it rigorous in this way, that it will work for these things.
But Eric, couldn't you do something like combining, if you have a less homogeneous graph, couldn't you just study kind of pockets where the infection stays for a long time and then see how it spreads elsewhere? I mean, could you do something a little bit more like that?
This is what people did when you have very heavy degree tails. They looked at what they called stars, and these stars were connected. And then, when one star dies out, the other one will infect them again. And, they could analyze and get these lower bounds. So that's also only enough for lower bounds. It's not possible to get some description of the normal distribution in that way. That's already too hard. And it's a lot of work and quite technical, whereas our kind of, coarse method gets better results, in fact, than those approaches. So, I'm doubtful if a detailed analysis will give us enough possibilities to make things stronger. I'm not sure about that. It's hard.
Is there any other question?
Yeah, Ines?
Yeah, if in what you call the critical case, when P is sigma over n, when you have that situation, I'm confused here, I forgot. Can you say anything about the size of the normal behavior of the infected?
I can have a pretty good guess, but I cannot prove it. So it's in fact, I've also worked on these kind of mean field methods. So these are non-rigorous methods, and we were able to extend. Usually they're only used to to get an idea of the average number of infections. And I know that in that case, the sigma over n case, simulations show that this mean field average is very good. Right? It's really quite close to where it should be. And then we extended these methods to get also an idea about the variance. And it turned out that those were even better. And furthermore, I could use this variance to correct the mean field average. And then the whole thing just kind of, was perfect almost. So we have ideas on what it should be. We just don't have any idea how to prove this, how to control this. That's the main problem. And we have all kinds of heuristic arguments why it should be like that, but there's no way to actually make it rigorous. And we need new ideas for that, I'm afraid. And
and did you see anything interesting coming up in the distribution of the infected nodes over the Erdos-Renyi graph? I mean,
usually it's not so interesting. It's just normal. The only thing that happens if Tor gets close to criticality, then you get other types of distributions, which are kind of skewed, usually towards the zero. Then different things come into play. And we actually have different type of graphs which are ideal for controlling in a certain way. And there we can show it, we can actually prove this. We can show that you get the normal when you have enough infections, but when you get fewer and fewer infections, you get different types of distributions. It starts to be deformed, the normal. So then you get what you say, interesting results, let's say. But in these random graphs, usually things are homogeneous enough not to get, for example, what's possible is that you have like 2 pockets of metastability. One with a lot of infected ones and then one with fewer ones. That's possible in principle. An easy way to think of this is when you have 2 components and, first both of them are still there and then one dies out and the other one is still there and you get different levels. But, it's a bit, it's not so interesting, of course, but it would explain why you can get different things and not only normal. It's possible to get different things.
Okay, I think that we should.
Yeah, we're a bit late
now. So let's thank the speaker again.
Thank you very much. It was my pleasure to see all of you again.
Anyone wants to say anything else? No. So I close my presentation. Thank you very much.
Thank you.
We can stay.
Okay. Bye-bye.
We don't need to record anymore. I mean, we can stop the